How's it going, everyone? Happy Thursday. Wanted to go ahead and make a quick video about how to do P2C. So sort of just an overview of how combinations work. So if you're sort of confused about how recursion works and how we can do this in LC2K, this overview should basically just cover how combinations work and then how we can translate that logic over to assembly code. So first things first, let's talk about, first of all, what a combination is and how we can think about it in terms of C code. So right here, I have this function called combinations. Let's go ahead and change this to N and R. So essentially, we're going to go ahead and calculate the combination of N comma R. And the way we can define combinations of N comma R, so let's just go ahead and say, what if we call combinations of N comma R? What is that equal to? What that is equal to is the combinations of N minus 1 plus combinations of N minus 1 R minus 1. So just a refresher about how recursion works. So you can sort of think about this like traveling down a staircase. So let's assume real quick that we are at the top floor of some building, right? We'll just go ahead and draw a door right here, some windows like this, and we're at the very top of this building. And we want to go ahead and basically find an answer to a question. Let's say, for example, we want to know what is the temperature in the basement of this building? Well, we don't know that because we're at the top floor. So we have to go to this thing called the base case, or in this case, the basement of the building, right? We're going to travel down a staircase, say, are we at the basement? No, we're not. Keep on traveling up until we hit this base case in the basement. And in that case, cool, we know the temperature, right? And then we can use that information to go ahead and build up and solve other subproblems that we to calculate. This analogy is kind of weird, but I think the way you can visualize this is sort of like we travel down this recursive stack, right? We travel down the building, and then we go ahead and we use our solution at the base case. So again, going to the basement in this case, and we can use that solution to go ahead and leverage future solutions, right? So I don't have a problem statement for this, but let's just go ahead and assume that we have to go to the basement. We find some information. We can then use that information to go ahead and solve maybe the problem on the first story of the building, right? And now that we've solved this problem, we can go ahead and solve this problem right here on the second story, and then we can solve the problem on the third story, and then we can finally use that information to solve the problem on this story right here, aka where we called the function from. So what does this look like in terms of combinations? Well, let's go ahead and talk about combinations of 3, 2. So I'll go ahead and say 3C2 like this. This basically just means combinations. So I'll say right here, combination of 3, 2. The way this works, and it's sort of like a tree question. So we first need to go ahead and determine, cool, combinations of 3, 2. What is that equal to? And that's going to be equal to combinations of N minus 1. I forgot to put an R right here. Sorry about that. This. So we'll go ahead and say combinations of N minus 1, which is going to be 3 minus 1. It's going to be 2. And then R is going to be 2 plus combinations of 2, 1. Again, all I'm doing here is taking the value we pass in. So 3 in this case, subtracting 1, 2, 2 minus 1, you get 1. So in order for us to solve combinations of 3, 2, we have to go ahead and solve basically, again, the building analogy. We have to go down a floor and solve that problem. So for this, we have to go ahead and solve 2 combination 2. And we also have to solve 2 combination 1. And then from that, we have to go ahead and solve those subproblems. The question is, when do we actually stop? Like, when do we stop recursing? In our analogy before, we talked about, oh, we hit this basement, right? That's going to be our base case. Our base case is basically saying, okay, we don't need to travel further down the building, right? We've already hit our base case. We now have a solution for a given step. So for the combination question, our base case is going to be if our R value is 0 or our value of N is equal to our value of R. So in this case, this right here is going to be a base case. That is because our value of N is 2 and value of R is going to be 2. So in that case, we can go ahead and say that, cool, 2 equals 2. That's our base case. There's no more recursion that has to happen at this step. However, this step, there's no base case, right? For 2, 1, that is because 2 is not equal to 1 and 1 is not equal to 0. So from this, we have to keep on recursing down, right? We have to go ahead and solve 1 combination 1, as well as we go ahead and decide 1 combination 0. These two are both going to be base cases. That is because 1 equals 1 in this case, so we can stop going down if we hit that basement floor. And then right here, R equals 0, so we don't have to recurse down any further. we can then use these solutions to be able to get a better solution, right? If I asked you, what is 2 combination 1? We don't know the answer, right? But if I asked you, what is 1 combination 1? We know the answer from the base case. So essentially what we're doing here is we're going to go ahead and say, cool, 1 combination 1, that value, I'll go ahead and use green for this. The value of this is just going to be 1. I'll put a 1 right here. Same thing for this and same thing for this. That is because they're all base cases. We also know, let me go ahead and pull this back up, sorry. That combination of 2 comma 1 is equal to combination of 1 comma 1 plus combination of 1 comma 0. We just went ahead and solved combination of 1, 1 and 1 combination 0 like this. So we know that this value right here is going to be a 1 and this value here is going to be a 1. So once we do that, we now know that 2 combination 1 is going to be 1 plus 1 in this case, aka a 2. We also know that combination 3, 2 is combination 2, 2 plus combination 2, 1. We've already decided what 2, 2 is because that was a base case. It's going to be 1. And we just went ahead and calculated a combination of 2, 1, which is going to be 2. So we have 1 plus 2, and it's going to give us 3. So our final answer is going to be a 3. Now, notice here how this is a tree question. And this is really important for understanding how our code should be structured. The idea here is we went ahead and we solved from left to right. And if you guys haven't taken 281 yet, don't worry about it. I believe we do cover trees in 280, but this is a good way to view the problem, right? Basically here, we want to go ahead and solve all of the left subproblems first. So we first went ahead and solved 2 combination 2. We can't solve anything else because it's a base case. So we go back up the root right here, and then we solve this combination problem right here, 2 comma 1. We don't know the solution immediately. Let's go ahead and solve its left leaf problem. So 1 combination 1, we solve that. It's a base case. Cool, return that. Solve the right problem right here. Cool, we solve that. And now we have a solution to this. And then we sort of work our way back up the tree. That's how we can visualize recursion in the sense. So if I were to run through on the actual C code, what's happening? Again, pull this to the side. Cool. Yeah. So again, we go ahead and we calculate combination 3, 2. So the combination of 3 minus 1 is going to be 2, comma 2, plus combination of, in this case, 2, comma 1. We go ahead and we next calculate this right here, combination 2, comma 2. We first go ahead and check to see, is it a base case? It is right here. So we go ahead, smile face, we're at a base case. Go ahead and say it's going to be a 1 right here. Next thing we do is calculate, again, this right problem right here. So we do combination of 2, comma 1 is equal to combination of 1, comma 1 plus combination of 1, comma 0. Let's go ahead and calculate this one first. This is going to be a base case. It's going to be a 1. And same thing for this right here. That's going to be a 1 as well. Consistent, I guess. Cool. We get a 1 right here, a 1 right here. When we return back up, we're going to go ahead and take these values of 1 plus 1, get a 2 right here. We've now resolved combination of 2, comma 1 to be a 2. And then we've already resolved this. So we do 1 plus 2. Now, this is where it gets a bit confusing. How did we know, right? When we returned from combinations 2, 1, how did we know there was a 1 right here? That can get pretty confusing, right? Like, where are we storing this 1 at exactly? Can we put it in a register? Like, what are we doing exactly? Here's the issue, right? If we're making, let's say, for example, 100 recursive calls, which you can on very large inputs, like 14 combination 7, then we don't have enough registers to use, obviously. We only have 8 registers, and most of them we're going to be using for, storing the values of n, stuff like that. So we really don't have enough registers to store values. So how do we work around that? What we're going to do here is use a stack. So the stack's a pretty powerful tool. So visually, what it looks like is, draw down here. We have our text, we have our data, and then we have our stack right below here. So our text is going to be our instructions. So let's say, for example, it's like VEQ 00, like label, right? A bunch of text, right? And then down here, we might have some data, like 1.fill1, all this stuff right here. Right below this is where our stack's going to live. And our stack is useful for saving information we need later on. So on the stack, we can save stuff like our current value of n, our current value of r, our address we want to return to, as well as what is our current solution so far. So let's go ahead and talk about how we can use a stack to go ahead and implement P2C. All right, so let's go ahead and work through the example of 3, 2, but this time we're going to visualize what's happening on the stack. So let's go ahead and put inputs in 3, 2. So the first thing we're going to go ahead and do, and this is the first step you should always be doing, check your base cases. So in this case, I'm going to put right here, n is equal to 3 and r is equal to 2. So what we're going to do first is check to see, are either of these things true? Does n equal r? Nope. Is r 0? Nope, it isn't. Cool. What we're then going to do, and I'm going to draw my stack. Let's do it right here. So the stack is so far empty, right? Remember, we have our text right here. We have our data right here. We have our stack. Our stack is going to have nothing on it so far. What we're first going to do is go ahead and save n to the stack. So I'll say save n to stack. So when I say n, I mean the current value. So it's going to be a 3. We're then going to go ahead and save r to the stack, which is a 2. And we also want to go ahead and save our return address. So return address to the stack. After that, we're then going to go ahead and calculate. I'll go ahead and put steps right here. There's a lot to keep track of. Sorry about that. Steps. So 1, save relevant. Can't spell. Save and save important info to the stack. Cool. So we do that. Step 0, I guess, is check the base cases. So again, before we actually save anything to the stack, we want to make sure, like, do we actually have to recurse further, right? In the case of, let's say, for example, 2, 2, there's no need to make any more recursive steps for that, right? We already know that 2, 2 is a base case, which means we don't have to go down any further. We pull this back up real quick. 2, 2, it had no like leaf children. It basically means that from that, there's no value it needs to calculate, right? It's a base case. Whereas 2, 1, it's not a base case, right? We have to know what 1, 1, 1, 0 is for us to calculate that. So again, 3, 2, check our base cases. They're not true. They aren't true. So cool. We'll go ahead and save nr and a return address to the stack. And we'll then go ahead and call a subroutine. So I'll go ahead and put this in real quick. Call subroutine. I don't know how to spell it. So call. You guys are laughing at me. I can't spell. Sorry about that. I think that's right. Cool. Who cares? Call subroutine to calculate combinations of n-1 r. So in this case, we have to go ahead and decrement n. So that's going to look like us basically doing something like, I'll put it right here, n equals n-1. And we're going to go ahead and repeat that process over and over again until we hit some base case. So in this case, what we did is we went ahead, we saved 3 to the stack, 2 to the stack, return address to the stack, and we went ahead and we tried to calculate 2, 2. Perfect. We jump into 2, 2. So our n is now going to be 2, our r is now going to be 2. Remember, 3 and 2 are saved to the stack, but our values, the registers that hold n and r, are going to be changed. So it's our duty to recover those once we return from this function. So once we do this, if n is 2, r is 2, we first go ahead and check our base cases. N equals r is true. So what we actually want to do here is, instead of doing steps 1 and 2, we're instead going to go, we'll go ahead and put indentation here. If base case is true, we are then going to load in the value of 1 into register 3. And then return back to return address. So what does that look like? In this case, it looks like we first went ahead and said combinations of 3, 2. That's not a base case. We're going to take these values right here, push into the stack alongside the return address. We're going to go ahead and say n equals n-1 and go ahead and calculate combinations of n-1 r. So go ahead and calculate combinations 2, 2. We check to see if it's a base case. It is a base case. We're then going to go ahead and the base case says return 1. So we're going to go ahead and put the value of 1 into register 3, just like that. So our next step is to go ahead and, after we calculate what this is, we return back to this, 3, 2. Remember here, we said the value of this is dependent on 2, 2 plus 2, 1. So we went ahead and we solved this for 1. The issue here, though, is that we can't guarantee that register 3 is going to be changed or going to stay the same, right? It's going to be changed eventually, right? Some other recursive call is going to modify the base case, and it's going to change that value. So we can't have that there. What we're going to do instead is we're then going to, I'll make this new section for combinations of n-1, r-1. For this, we're going to go ahead and push our result of register 3 to the stack. It's sort of like our running total so far. So in this case, that's going to be 2, 2, right? That's what we have so far. There's 2 parts to making combinations 3, 2. There's n-1 r and n-1 r-1. We've gone ahead, we calculated n-1 r right here. We went ahead, we put that inside a register, and then we went ahead and then pushed that to the stack so we can use it for later, right? So now we don't really care what's inside register 3, so I've gone ahead and pushed it to the stack. So go ahead and put this right here. Push reg3 to the stack. So in this case, it's just going to be a 1. After that, what we do is we go ahead and calculate n-1, r-1. We've already had n decremented to 2 right here. We have to go ahead and decrement r to be a 1. And then we go ahead and calculate again, right? We're now looking at this function right here. We are now in this scope, right? Let me go ahead and get pen color out. Feeling orange. There we go. We're looking right here. We have to go ahead and again, repeat that entire process over again. We first go ahead and look at the left leaf and then the right leaf. So the left leaf, we're going to go ahead and again, look at this right here and check our base cases. This is a very hard thing to grasp. I'll make a few analogies here. There's this idea called the recursive leap of faith. And basically that means when I'm saying combinations of 2, 1, I'm sort of saying, okay, cool. I don't know the answer yet, but one of my base cases will, and they can build up a solution that I can use. So even though there's no solution to 2, 1, we're basically calculating that on the fly. And once that we get a return value that is some number, right? Once 1, 1 returns, we can then go ahead and calculate 1, 0, and then we can go ahead and get an answer. And that's the goal. We don't immediately know the answer of 2, 1. We have to go ahead and keep on recursing further and further down until we hit a base case, or in the building analogy, we go down enough staircases, we can go to the basement eventually. We can hit the base case. So we go ahead, we go to combination of 1, 1. We do these steps now because we're calculating n-1 r. So we first go ahead, check our base cases, n equals r. We repeat that exact same process over again. So in this case, we go ahead and again, we put 1 inside register 3. So push reg 3 to the stack, which is going to be a 1 in this case. And then we go ahead and calculate n-1 r-1. So we decrement r. So we're going to go ahead and change. Sorry, this should be a 1 right here. Go ahead and calculate r. It's going to be a 0. And from that, our base case will fire again because r is going to be 0. So in that case, we go ahead and this is where it gets a bit tricky, right? We can now combine 2 solutions into 1. The question is, how do we do that? Remember, from n-1 r, we went ahead and we pushed our current solution to the stack, right? Look right here. Save current result to the stack. So when I return from 1, 1, I put a 1 inside register 3. And before I did any calculations here, I went ahead and I pushed this 1 to the stack. So our stack has a 1 in it right now. When I go ahead and I return from this base case right here, it's going to be inside register 3, right? The base case result is. So what we're doing here essentially is we're going to say the value inside reg 3, which is kind of in sense the return value of combinations of 1, 0, plus the value, let me go ahead and indent this, on the stack so far. Remember, we push this 1 to the stack. So we have to go ahead and pull it off the stack, right? So what does that look like? So basically we have the stack pointer. And the way this works, our stack again begins at m plus n, where m is the size of text and n is the size of our data. Sorry, m is the size of text, n's data, cool. whenever we add something to text, we have to go ahead and have a stack pointer, which basically keeps track of where are we currently at in terms of like what level of the stack are we at. Whenever we pop something off the stack, we're going to go ahead and basically get that value and decrement our stack pointer by 1. If we want to go ahead and add something to the stack, we'll go ahead and add 1 to our stack pointer. So in a sense, what we're doing here is we put it on the stack. It's like right here. We go ahead, we grab it, and decrement our stack pointer. So now we're down here. Cool. So we go ahead and we go ahead and make this a bit cleaner. Let me erase all this stuff. Cool. So on the stack, we have this 1 floating around from this right here. Draw an arrow right there. We just went ahead and we returned from this function right here. We returned a 1 inside register 3. That's an R, by the way. Cool. Register 3 has a 1 in it, like this. So if we go ahead and take register 3's value plus the value in the stack, we're going to get 2. And that's then going to be the value of this right here. After that, we can then go ahead and take this 2 right here and add it to the next value on the stack. So this 2 right here plus the 1 on the stack, and then we get 3. So it's a bit confusing, but I'll just go ahead and highlight real quick what we just did. Let me go ahead and erase all this stuff real quick. Cool. Would I erase? Should be a 2 here. Yeah. Okay. So we started off by saying we want to go ahead and calculate combination of 3, 2. For us to do that, we need to know the answer of combination of 2, 2 and combination of 2, 1. So let's go ahead and work from left to right. We first go ahead and we solve combination 2, 2. We first check to see if the base case is hit. Base case is hit. So we go ahead and we put a 1 inside register 3, return that value back here, and put it on the stack. We have a 1 right here. We then go ahead and we are concerned about this part of the function now. Once we get to here, we go ahead and repeat that exact same process over again. We go ahead and we calculate what combination of 1, 1 is. Again, it's a base case. So we're going to go ahead, take this 1, put it inside register 3, return back over here, and then put it on the stack. So I'll go ahead and put this as yellow. That's going to be that 1 right here. And then we go ahead and we calculate the right-hand side. The right-hand side is going to be a base case right here. 1C0 is going to be a base case. So we're going to go ahead and put a 1 inside register 3. It's going to be a 1. And then we're going to go ahead and say combination of 2, 1 is going to be equal to register 3's value plus the first value in the stack. That's a value, right? On the stack, remember, we're also saving our value of n, value of r, and our return address. I'm not drawing it out to make it seem a bit easier, but there are going to be other values here on the stack, so consider that as well, like what position they're at. So it's a really good idea to go ahead and be consistent about how you push up to the stack. So maybe you're pushing n, then r, then return address, and then maybe the value of something if you have it there. Just be consistent. So we have R3, which is going to be a 1 in this case, plus this value off the stack. We're going to pop our stack right here, put it right here, get a 1, and then we have 1 plus 1 is 2, and that's going to be inside register 3. We then went ahead and popped this value off the stack, and then we, again, are sort of like climbing back up the building. So we go ahead and go back over here and say R3 plus this value right here on the stack. R3 plus 1 is 2 plus 1, and that is 3. And then we return back to where we were called from. So I hope this helped you guys out a little bit. If you have more questions about it, feel free to drop in the comments. I'm trying to think if there's anything else that's helpful to talk about. I can't think of any. My main tips for the project, again, understand the base case and what stops recursion. Going back to the tree example, remember how we went from left to right. We started calculating n-1 r, and then once we did that, we went ahead and started going to the right tree, and then we started going to the left as much as we could. By the left, I mean we try to calculate n-1 r first, and then we try to calculate n-1 r -1 first. We're going ahead and we're building up small solutions to go ahead and solve the bigger problem. Base cases can combine to go ahead and essentially solve the problem. One pattern that's helpful to observe too, is going back, can I Control Z this? Okay, I cannot. So if I have 3, 2, right? Like this. Remember, its child over here is going to be 2, 2, 2 choose 2, 2 combination 2, same thing. Over here, we had, what was that? 1 combination 2, which is going to have children. Sorry, it's 2 combination 2. No, sorry, 2 combination 1. There we go. And that's going to be 1 combination 1. And this is going to be 1 combination 0. The right, and again, this is like not needed for the project, but it's helpful to like visualize it this way. The right-hand side of the tree in this case, they're both going to be base cases. This is the only instance where it will happen, where they're both going to be base cases. In this case, this value is going to be a 2, right? Because we have 1, 1 right here. Again, we save this value on the stack and add to this value, we get a 2. And then once you solve this part of the tree, everything else should already be solved, right? Because we already solved this left-hand side of the tree right here, right? We already said this is going to be a 1. So all the work's being done. We're just returning now and adding, we're popping up the stack, adding that to our current value, returning, adding value from the current stack to our current value, returning, and we repeat that process over again. We're essentially saving the left-hand side of the tree to the stack the entire time. Everything over here is going to be on the stack, essentially. And when we return, the right-hand side is basically saying, I have a current solution, I'm going to add the stack to it into one solution, and then go back up the stack and pull the next value and add to that. And once you understand how that works, the program becomes so much easier to write. So my advice for writing the program is check base cases, calculate n-1 r, calculate n-1 r-1, and then combine them and return. So returning back to the previously function that called it. So in the case of 2, 1, we had 2 children, right? We had 1, 0, and then, sorry, we had 1, 1, 1, 0, both base cases, right? Those 2 combined into one function, right? Some function called those 2 other functions, right? We have to return to the function that called that and then build a solution up from that. So I hope that's helpful. Any questions, drop it on Piazza. It's due on Tuesday, I believe, on the 26th. So you guys got plenty of time to do this. Good luck. Yeah, any questions, drop them in the comment section, Piazza. I'll be sure to look at them. All right, good luck in the project and the exam.